hosts, Seymour and Esther Padnos College of Engineering and Computing. I'm Brent Nowak. I'm the Executive Director of the Applied Medical Device Institute here at GVSU. And joining me today are Rick Shorey, Vice President for R&D at Medisurge, and John Hall, our Principal Engineer at aMDI and Program Manager. Before I get started, let's go ahead and cover a little bit of the logistics. You know, we've designed this webinar intentionally to be 30 minutes. And what we're looking at is, I want to point out that we're going to be taking questions and answers at the end of this seminar. So make sure as we're talking, because this is a very fast-paced webinar, we want to, we value your time and want to make sure we use it appropriately. Just type your questions in and we'll take those questions and answers at the end. If you can't stay for after the 30 minutes that this was designed for, that's okay. We're going to stay live and continue answering those questions. And this is going to be a recorded session, so you'll be able to come back later and watch the complete webinar or go to the questions that were unanswered at the time that when you had to leave. So again, welcome. The last thing I want to do is make sure that everyone understands that all the questions and answers can be seen by everybody, so feel free to share whatever you want. It may stimulate some additional questions. So without any further ado, I'll go ahead and get started. What I want to do first is introduce you or do a quick summary of the additive manufacturing industry. Additive manufacturing began about some 30 years ago. Now it has matured. It's a complex, multifaceted industry. In about 2019, it was somewhere around a $10 billion market. When many people talk about 3D printing or additive manufacturing, they think about the machines. And you can see on the slide right there that there are numerous categories of original equipment manufacturers in the polymers, whether they're desktop machines or metal machines. And now we're seeing more companies enter into ceramics, microelectronics, and also biological 3D printing. But there's 50 plus companies out there. But in reality, the industry has a strong backbone in software, which is really a enabling technology for additive manufacturing, as we all know. So you have the players in design and CAD software, simulation software, but now, as additive manufacturing becomes more and more of a production system, you have the workflow software, where you can have multiple machines in the manufacturing line, and those have to be scheduled. And finally, we have the suppliers of materials, which are critical to additive manufacturing. And that industry, in both polymers and composites, is booming as well, as more and more suppliers are coming online, trying to drive the cost down, giving us more variety of materials. And we'll cover more of that here during this seminar or this webinar. Of course, there's also the post-processing, the IQ people, and the research institutes that are driving that cutting edge of the additive manufacturing. In 2016, there were two different surveys I looked at they showed only about 24% of the companies, the 2,000 companies worldwide that were surveyed, had ever used additive manufacturing. 3 years later, that number was already up to 65%. In 2020, that's even larger. North America leads the installations with 422,000 installations, more than any other segment of the global market. And a third of those companies that were surveyed above are actually producing functional parts, not just for innovation and prototyping, but they're building end components, tools, spare parts. So this additive manufacturing is driving itself into the production environment. North America also leads the world in the most additive manufacturing headquarters. So it's very key to what we do here. And as everyone knows, it's part of Industry 4.0. From the economic development standpoint, it's critical to understand that every dollar spent in manufacturing brings in $1.8 back to the economy itself. So many of us who are on this webinar, either the participants, the panel ourselves, but also those viewing or adding, why would I want to invest in additive manufacturing? Well, that depends on what your corporate strategy is, and we won't spend a lot of time on that in this webinar, but future webinars. The question is it performance? Are you an innovating company or you just want to grow? Well, the key question that we wanted to study in this webinar, to review in this webinar, but also part of our 3-year study, is where's that threshold between conventional manufacturing, which is the curved line, where we see the cost of manufacturing on the vertical axis per unit, and the units created or units manufactured on the horizontal axis, where the conventional manufacturing has that steep curve that drives the cost down as you increase the volume. Additive manufacturing is not necessarily a horizontal line, but it's much more linear. And the question we're trying to study today is where's that breakoff point, specifically with regard to the med device market. So what we did, Medisurge and the Applied Medical Device Institute through Grand Valley State University and the MEDC in the city of Grand Rapids created what's called the Public-Private Partnership. This is a 3-year program where we're looking at, first, we studied the additive manufacturing market in depth in all the fields we talked about, the software, the additive manufacturers, original equipment manufacturers, plus materials and suppliers. We selected a carbon 3D system, which we're going to talk more about in a minute. The second year, we renovated the facility. We did the installation, training, and commissioning, where we began some early contract production manufacturing. And year 3, which we're entering now, and these years cross calendar years, but as we enter now, we're getting into a full service providers. So in summary, what we're addressing today is additive manufacturing as a production system in the medical device market. So without any further ado, let me introduce our speakers. First, Rick Shorey. As we mentioned, he's the Vice President of Research and Development at Medisurge. He has an enormous amount of work in the med device space, both in management and research and development, product launches, et cetera. Now, John Hall, as well, has got an enormous amount of work in the med device world. He's worked at several large med device product manufacturers, as well as Cleveland Clinic, numerous number of patents, and also he is a voting member of the ASTM F42 Committee on Additive Manufacturing. So with that, let me go ahead and hand it over to our presenters today.
Thank you very much, Brent. I appreciate that, and thank you to those who are participating in the webinar today. I first wanted to start off with a very high-level, quick overview of the different types of polymer additive manufacturing. And there's a lot of different technologies here, but there's 4 primary ones that are the most commonly used today. And the first one that I want to cover is material extrusion. This is probably the one I think that people think about the most often whenever they think about 3D printing. And basically this is like a miniaturized extruder. Common terminology that's used for this is fused deposition modeling or fused filament fabrication. The company that really, was the workhorse of this industry for a long time was the Stratasys Dimension and their Dimension family of printers. Basically this, produces thermoplastic parts, one layer at a time, and good, quick ability to make these parts. In the expensive, there's been a lot of development of additional manufacturers in this technology recently, and there's a lot, companies now that you can buy this type of equipment for a few $100s up to maybe 10,000 or more. And the key thing with this is that you can get simple thermoplastic materials. It used to be just ABS that was available, but now there's a lot of other material options. But they often have a adhesion issue because of the nature of the process, between as the layers get built on top of one another. The next area that I want to talk about, the technology, is powder bed fusion. This method, as it sounds, is basically a bed of powderized thermoplastic material that gets fused together for the part, either by laser sintering or laser melting. And more recently, HP has developed a really nice printer system, multi-jet fusion, which has a large print volume and in really good high resolution and lots of good thermoplastic material options. The next technology I'd like to discuss is material jetting. A couple of companies that are heavily involved in this area are PolyJet, which is part of Stratasys, and PolyProjet, which is part of 3D Systems. This technology utilizes depositing small droplets of photoreactive resin and then immediately curing it, typically with a UV light source. Again, this technology has really fine, good resolution and a fairly quick print time. And then the final technology for polymer additive manufacturing that I wanted to discuss is vat polymerization. And this is really the technology that kind of birthed the whole industry of 3D printing. Back in the 1980s, 3D Systems developed a stereolithography system. And then in the coming decades since then, there's been a lot of really good technology advances that have improved the process. And just a couple I'm highlighting here are the digital light processing or synthesis, which basically is a projection of the entire cross-section of the build platform at one time So you get that whole cross-section cured at once, and you don't have to trace it out with a pinpoint laser. And then the other technology here is the continuous liquid interface production. And this allows, really good, continuity between the different layers in the Z print direction, which allows for you to have, functionally equivalent mechanical properties regardless of the print direction. Next. So I just wanted to cover here real quickly before we jump into some more details about the program is what some of the significant advances in the liquid photopolymer additive manufacturing have been in the last 20 years. So you can see the picture on the left side of the screen here is a 3D system, Viper system from around about the year 2000. This was really state of the art at that time. And then on the right screen, you see a picture of a more recent technology from Carbon 3D M2 printer. And so the key things that have really changed in the 20 years is that the print times have gone down dramatically, and that's largely related to the projection technology. The material properties have also gotten a lot more consistent, and there's a lot more options now. So you can have flexible materials, you can have high temperature materials, high strength materials. Another significant change in the polymer additive manufacturing is that both the equipment and the resin cost have gone down significantly. And I already mentioned about the mechanical properties and the ability to have a part that's isotropic or functionally mechanically equivalent in all different directions coming off of the printers. And the mechanical properties are a lot more stable now as well. And then the print resolution has gotten a lot finer. You can print a lot smaller detail now than you could in the past. And then lastly, the build direction has changed. So it used to be that as the part grew, it was submerged into the vat of photopolymer. Now the parts are printed upside down, and as the part grows, it's actually pulled up out of the liquid vat of resin. Now I'll turn it over to Rick to talk some more about our collaborative program.
Thank you. Hello, everyone. So I'm going to talk a little bit about our program outline and the decision process, as well as our cell layout. So on this slide, you can see the timeline that was laid out. Brent alluded to a 3-year program. We added a couple of years on this timeline. The plan going forward is to go into more of a scalable production situation. But starting in 2018, looking through the grant proposal, research on the machines, etc., into installation, training, capability on production side, and then ramp up. So what was our selection criteria? So going for this particular technology, we needed something that would be scalable for contract manufacturing. That was the key for us. We wanted to look at this from a CM standpoint, like how is this going to work for us? It had to be compatible with existing manufacturing processes. So with polymer-based components, it needed to be bondable, sterilizable. We could put this together with UV adhesive or even snap fitting. Cost competitive with regard to the machine, obviously, and then good customer support from the company that we selected. We think we found that. In addition, we wanted something that had significant material versatility for med device. If you're in med device now, you understand that you can have anything from a very soft material to a very hard material, and they all have to perform equally with regard to user interface. So we did select the Carbon 3D machine. It is a clip style printer. It does have a small footprint. It does have isotropic part fabrication, which we confirmed via a master's degree defense of one of our graduate level students in the past year. The materials for the carbon range from cyanate ester, which is a machine grade material, to polyurethanes, which are typical for med device fabrication, and also silicones. These materials are bondable and sterilizable. They are biocompatible with regard to ISO 10993. So that testing has been done by Carbon, and it is available to customers. It does have a large range of materials. We'll talk a little bit more about that later, but anything from very soft silicones to very rigid machine grade for fixturing. The particular machine is also designed really well for cell layout and scalability for contract manufacturing if we wanted to add multiple machines. Next. So our additive manufacturing location that we currently have set up based on the private partnership, the installation was in February of 2019. This is a satellite extension of the Medisurge contract manufacturing facility. So it is capable of manufacturing clinical use components today. It is set up for one-piece flow. You know, you may have gotten a little preview behind John Hall. He's in the laboratory where the cell is set up today. Training and talent development. So we've got at least 15 employees trained on the Carbon Academy, so they've been very supportive with training with regard to not just additive manufacturing, but also the use of their machines and post-processing. There's 150 modules involved with that. It takes about a week to get through, so it's quite involved. You get a certificate at the end. As I said, we've got a master's thesis that's been defended on the idea of isotropic material, isotropic part fabrication, meaning that it's equivalent to a fluid version of an injection molded part, something that would be, you know, equal in performance in any direction. We do have the Additive Manufacturing Student Learning Center for Grand Valley State University, which has been valuable to GVSU and the students as well. We have received production RFQs and we've quoted out parts. We are small volume capable today. Next. So just run quickly through some of the targeted benefits of additive manufacturing, some of the things that we've discovered, and some of them are inherent as well. So cost is one thing that isn't necessarily inherent with additive manufacturing, but what I can say is that the initial capital investment for this type of technology is eliminated for such as injection molded tools. So you get an improved return on investment because you're not investing that capital equipment up front. It is a faster development time to market because you're eliminating that time frame with the iterative process through tooling and tool manufacture or tool making. And so you can get to design testing much quicker. There's minimal material waste with 3D additive manufacturing, and also you can decrease your inventory with on-demand builds. So that's something that we talk about with one-piece flow and on-demand flow. It's a huge benefit potentially going forward. There's decreased design limitations with additive manufacturing. Of course, this is everyone knows this. You can do lattice work, undercuts, hollow outs. It doesn't really put any handcuffs on you with regard to design. The iterative design process is inherent and it's minimal cost. So you can do design one day, test it in the afternoon, make a change to the design, and have another part the next day to check. So that's something that's very quick turnaround. And then the last thing is prototype and production parts are concurrent. And what I mean by that is that you have production equivalency on day one. And so with a material that's already biocompatible, for example, that has multiple durometers that I can choose from as a designer or as a developer or manufacturer, I can prototype a part today. I can have it to the laboratory to test tomorrow. And that's going to be the same part that's made 6 months from now in production. So that's significant when it comes to things like FDA submissions. Next. So we're going to walk through with regard to part cost. I mean, that's always the big question with additive manufacturing. Of course, the tooling cost is eliminated, but what's the part cost? And that's always been the challenge. Can you get to the point where we're competitive? So we're going to run through a few case studies. I'm going to start with this one. It's called a fluid manifold. Next. Next. Thank you. So this particular product is used in platelet lysate handling, material handling for laboratories. This subassembly was built with 7 different components, and there are 6 glue joints involved, and it's all manual gluing. So this is also a product that we had to pull test and process, and with design validation. And there has been, from the customer, a confirmed risk of separation in the field. And if that happens, certainly it is a recall situation, or more serious than that even. So the total cost of this subassembly as is $27 approximately. Next. Next slide, please. Brent, can you advance the slide? Okay, thanks. Sorry about that, guys. So what we did with this particular assembly is we went to a direct replacement using additive manufacturing. So we reduced it from 7 components to 1 component in this particular situation. Obviously, there's no gluing required with the new design. It eliminates the human error and also glue failure issues. It's functionally equivalent to the original design with regard to interface. And then we utilize the biocompatible material for this. So there's no issues with compatibility with the internal fluids. It also eliminates the risk of separation in the field. So this is something that the customer can go back and adjust their risk management program for. The total cost of this particular iteration was $26.58, so a reduction of about 43 cents. Next. So we took it to the next step, and we went to an optimized design with additive manufacturing. So we reduced the total volume of material and material costs. It has equivalent performance to the original replacement, and the interface with the machine is still identical to the original subassembly. This provided us with a 46% material reduction by weight and the cost of $20. So about a $6.75 reduction in cost over the original assembly. So this is a good example of something that does work with additive manufacturing. It's a very unique design. It's complex. It falls right into the wheelhouse. This is also a pretty low volume product for our customer. So it's something that we can build and manufacture and produce for them at an effective level. Next.
Thank you, Rick. That was a great example of showing one of the benefits you can achieve with additive manufacturing of part consolidation, right? So that example that Rick just shared, that part went from 7 different parts down to 1, which is something that would be very difficult to try to do that in traditional manufacturing. The next case study that we wanted to share with you is an introducer hub, and this one is going to speak more to the kind of size of part that fits well within the build platform for additive manufacturing. So an introducer hub, there are 3 images on the top there, just sort of different views of this. This is typically a part. Can you go back a slide there, Brent? All right. It's introducer is typically hub is bonded into a extrusion that is tipped, and then that gets used to help put a device into a patient. Traditional injection molding approach for this type of a product, a prototype, single cavity prototype mold would probably be in the range of $8,000 to $10,000. That would achieve you a part cost probably around $1 a piece. The minimum order quantity likely to be 500 or maybe even 1,000 parts. The lead time to build this mold would be 4 to 8 weeks. And then you probably would also have another 4 to 8 weeks if you were going to be, going from for ongoing production runs. And if you look at the additive manufacturing approach, this part's about the size of the end of your thumb. So you can fit, I think there's 84 parts that are shown on the build platform there on the image on the right. The nice thing here, right, is you've got no mold cost. And with this particular, part, the build time, I think, is a little over an hour. So you can basically build about 84 parts in an hour. You get a part cost, fully out for production quantities of about $3 a piece. Lower minimum order quantity, basically one build platform. And your lead time is only a couple of days for that. So the next thing, just to kind of think about where the balance point is here for this additive manufacturing is, if you're above 5,000 parts, then, or below 5,000 parts, then it's actually less expensive to use additive manufacturing for this component. And sometimes, these medical products take a little bit of time to take off. So if you only have a 500 piece volume in your first year, you'd actually save $9,000 to the additive manufacturing. And another important thing to think about with this type of product as well is there's often a lot of different versions. You may have half a dozen different extrusions that you want to bond into this hub. For traditional injection molding, then that will require more expense for core pins and then changeovers, to switch between the different versions. With additive manufacturing, there's no additional cost for those different versions. And if you wanted to, you could even put actually multiple versions on the same build platform. Next. Brent, next slide, please. The last case study that we wanted to cover today is actually one that doesn't really make sense for additive manufacturing. But we thought this would be insightful to share with you because we did look at it in both traditional and additive manufacturing. So our client wanted us to design a custom wall faceplate. I have one shown here that's just a light switch, but it's basically the same size and a similar type product. Next. So looking at the injection molding approach for this type of a product, if we can get to the next slide. The prototype mold for this would be around $9,000. Yield a part cost of about $1 each. Again, you have that minimum order quantity, probably 500 to 1,000 parts. Lead time to build the mold, 4 weeks, and then this client actually was looking specifically for 1,000 pieces for their first production order. So your cost for that, doing a traditional injection molding, would be around $10,000 for those first 1,000 pieces. And now, if looking at the additive manufacturing approach, zero mold cost again. This part's a good bit larger. It's about the size of a note card. So we can only fit 10 of these on a build platform at one time. So that drives the part cost up to about $17 each. And then, maybe even more importantly, since you could probably only do about 3 builds in an 8-hour day for this particular part, you'd be looking at a lead time of almost 6 weeks to build 1,000 units, and the cost would be $17,000. So just thinking about here, this illustrates the point that, the traditional injection molding was more cost effective, for this type of situation. And also, it's actually easier to color match with injection molding. With liquid photopolymers, you're a little bit more restricted in your color options. And then, I would like to point out, though, here as well that, additive manufacturing was still a very valuable tool in this development program because it allowed us to quickly iterate on the design and get to, the parts that that ultimately we ended up doing injection molding for. Next slide, please. So just to recap, Carbon 3D M2 printer technology incorporates digital light synthesis or processing, as well as clip technology. This really allows you for quick print time and for that isotropic mechanical properties regardless of the print direction. We have 3 prototype materials that are available here. And we typically encourage clients or customers to first print their part in a prototype material so we can get an understanding of the layout and how it processes. And then we have 8 engineering materials. The harder materials, the MPU and the RPU, materials are available. There's also machinable as well as high strength materials, the EPX and the CE material. The CE material also is a high temperature material. It has a heat deflection temperature of, I think, 230 Celsius. There's more flexible materials as well. EPU 40 is similar to a thermoplastic elastomer. And then FPU 50 has some properties that are similar to polypropylene, so it's suitable for things like snap fits. And lastly here, well, the last two materials here we have is a elastomeric material, the SIL 30. And then there's a FDA approved dental material called Keysplint Soft Clear, which can be used for custom mouth guards and appliances. And as Rick mentioned earlier, all of these materials have passed biocompatibility screening that was provided by Carbon.
Great, thanks, John. So just to recap on the benefits and applications, so this can provide you with reduced capital investment, on-demand builds, instant iterative design capabilities. You can get your products to market faster. It gives you design freedom, and then a production equivalency from day one. So those are very important points to note. Still working on the cost piece of it, on the unit pieces, and this whole break-even point that we described in the beginning. Medical device applications for this, of course, this list is not comprehensive, but single-use sterile and non-sterile medical devices, dental, diagnostics, manufacturing fixtures, instruments, orthopedic, and therapeutic as well. So lots of opportunities there, and it gives you the freedom as a manufacturer or as someone that hires us as a CM to do many things on one particular machine. So it's very exciting.
Thank you, John and Rick, for that summary of what's happening in our study. Just want to remind everybody our focus was in that inflection point where production and prototyping between conventional and additive manufacturing plays a role. I want to let you know that we're going to have a number of future additive manufacturing webinars that cover this whole wide additive ecosystem. In addition, before we leave, if you have to leave now, we understand, but here's the contact information for John Hall and Rick Shorey. We thank you for attending. If you are able to stay, we're going to move on into the question and answer period now, and I'll go ahead and call up the questions, see if I can get those on my screen. Maybe those can be shared by the host up there. Here we go. So we have one question. The first one is Carbon 3D or equivalent additive manufacturing suitable for scaled manufacturing medical devices by an original equipment manufacturer or contract manufacturer? So John, you're the industry partner in this public-private partnership. Maybe you want to take the first stab at that question.
Sure, I think maybe we'll let Rick address that one.
I'm sorry, yeah, Rick.
Oh, no problem. So I think that's a question that's answered best by the application. And so, is it suitable? Yes, I think in situations it is. I think we've shown through some of our case studies that it can be applied. It can be applied well. I think that there certainly are places for this today. And as the costs come down, the platforms grow, and from John's slide on the hubs, for example, we can put something like 60 hubs on one platform. What if that platform was 5 times that size? Now you've got a 2-hour print, and you're getting 1,000 pieces off. So now you're really in the ballpark when it comes to volume-based manufacturing, and cost-wise, your costs are just going to drop even more. And also, as the materials drop in price for the additive manufacturing, the costs will come in. So I think there's a place for it on the traditional front for all additive manufacturing arguments. The freedom to design, the iterative nature of it, your ability to go straight to design validation. But in addition, I think the costs are going to continue to drop. John?
Yeah, I think those are all great points, Rick. I think the one thing I would add as well, and is that the areas I think that we've found that additive manufacturing really shines are part consolidation, like the case study that Rick shared earlier. Also, the ability to have customer patient specific prints, and then the other area which we didn't really talk about at all in this webinar was part lightweighting. So when you can replace a solid structure with a lattice structure and take out 50, 60, 70% of the weight and still have the same strength, that's a real benefit and lowers the cost. And in some cases the weight of parts is very critical. So that's definitely an area where additive manufacturing shines.
So do we have another one, Brent? I see.
Yeah, we sure do. I apologize. We're having some audio problems here. As we all know, in this new world of video conferences and dealing with remote operations, I apologize. The next question we have is from Lindsay Cornell, which is similar to the last, but how does a traditional component manufacturer like injection molder or CNC machining fit into the additive manufacturing picture? And I think I'll take the first stab on that. It depends on what the strategy is for the injection molding company or the additive manufacturer, the CNC machining company. I know that you can rapid prototype pretty quickly molds with 3D additive manufacturing, and whether you're going to grow your company as an innovator, if you want to grow it in a new market, those all play a factor in that. But then again, going back to Rick as a contract manufacturer, how would you add to that answer?
I'd say that it fits in perfectly. I mean, these are technologies that are familiar with material handling, component manufacturing, first article inspection, validation of individual components on a high volume level. So it might be a slight change in direction for them, but it's a great precursor to high volume injection molding. I mean, it's a great precursor to, for metal additive manufacturing, for example, it's a great precursor to CNC machining in high volume. And you can ramp up and offer your customers a lot more versatility.
Yeah, I think, I couldn't agree more with that, Rick. I mean, this is a disruptive technology, sure, but it's not going to replace traditional conventional manufacturing methods. No, not at all.
It just adds a capability. And that's everybody wants more.
Yeah. Right. John, if you have anything to add, I'll move on to Brian Groger's question on USP 665. He's asking me to clarify that. That was to Rick. Is that something you mentioned earlier, John?
I think the original question here was related to what level of biocompatibility have these resins been tested to. And I'll try to take a shot at that. I'm actually not familiar with the USP 665, but I know that Carbon did their screening and testing to the ISO 10993 standard, and I know that they tested I think the NPU 100 to the furthest extent. I don't think it went through all the way through like implant or anything like that level of testing, but they completed a larger level of the biocompatibility screening test with that resin. But all of the ones that we had listed in the webinar, have at least undergone the initial base level of biocompatibility screening, which is included for things like skin contact and short-term duration. So I think trying to compare it back to USP, it's probably been tested at least to a level similar to like what used to be called USP Class 6 biocompatibility testing.
Right, I would agree.
And the other thing I would add, I guess, as well, is that the dental material that we have, the key splint soft material, that's handled a little bit differently by the FDA, and they actually approve, materials specifically for use in dental applications. It's different than in the medical device area where, the device itself gets approved in biocompatibility as part to support that device approval. In the dental area, they actually approve specific materials for use in the dental field, and that key splint material has been approved by the FDA for use in dental applications.
Thanks, John. Thanks, Rick. The question about next from Aaron Reichman is, you see additive manufacturing being used at the end user. And again, this is a case-by-case basis. I think that we've seen the articles speculating that you might have end users at the home may have additive manufacturing at the home. But I know today there are, in the case of the Navy, they have shipboard additive manufacturing in metals for spare parts. So it depends on the application. Remote operations where you don't have a very continuous or a high-risk supply chain, that would make sense. But in day-to-day operations, of course, we're seeing the desktop systems that are showing up in high schools, even junior high schools, and at homes. But on an industrial side, is there anything you might want to add, Rick or John, to that answer?
Yeah, absolutely. I think it's common today in a lot of dental applications. Additive manufacturing is used on site. That's the new thing, right? You go in and get your crown is made right on site. But also, in dental applications that we've seen, things like nighttime night guard appliances or TMJ appliances by the end user potentially. So absolutely full scope from basic high volume contract manufacturing to the end user. The other piece I think that John hit on a little bit is that end user, if it's a doctor-patient type of a situation, a lot of times, additive manufacturing could apply to customized devices. Let's say custom knee braces or customized joint therapy, things like that. That's a future type of application where it could be at the end user.
Yeah,
that makes sense. Go ahead, John.
Brent, I'd just like to add too that I think we are certainly moving in the direction towards the kind of science fiction idea of press a button and the part comes out. But there still is a lot of learning and understanding and know-how that needs to be developed in order to operate additive manufacturing equipment. So I think there's still a skill base that needs to be developed in order to produce parts efficiently, effectively, and reliably.
Oh, I wouldn't agree more than you just said, John. There's always that in-house expertise that's needed, which is why you need organizations like Medisurge, who are contract manufacturers that are experienced in medical device packaging, sterilization, assembly, clean rooms, et cetera. Yeah, there's applications where it doesn't make sense, or maybe someday where there's applications it does make sense. Or having people that have the design and theoretical knowledge and applied development knowledge, like at aMDI. So yeah, there's a balance between when will this become, truly, end user use. Now, that last question again by Aaron, I think plays along the same line. He's asking, do you think hospital or care facilities in the future will have additive manufacturing in-house? Or will the state of manufacturing companies? Again, that depends on the trade-off between volume and custom parts. But then if you do have a 3D additive manufacturing system in the healthcare space, the regulations are rigorous, to say the least. So that would be a big challenge, I think, for most hospitals to try to put in something like that. But I'll let Rick and John add to that.
Yeah, that was exactly what I was going to say, Brent. So if the rules are the same for manufacturers and hospitals, it would be very difficult for hospitals or care facilities to put in place any type of volume manufacturing using any method, frankly, whether it's additive or not. You have to have your QMS in place, and you have to manage the part builds and lot quantities and lot numbers and things like that. That's why we do what we do. But I'd say it's possible from a customized device standpoint. We see that in the dental world right now, so there's no reason to think that it wouldn't expand into, hospital or care facilities for things like class 1 devices or therapeutic devices that are not invasive.
Yeah, I agree with those comments as well, and I think the thing I would add there as well, I think it's probably very dependent on the institution as well, and how much they're willing to invest in, developing the skills and the personnel to be able to operate that internally.
Thank you. So I'm going to click over to the answered questions, see if we make sure we didn't miss any. But the last question here from Eunice Outerfot is, do you share the recording of the webinar? And yes, we absolutely will. This is recorded, and we will be posting that. Our PowerPoint presentation as well be converted to a PDF format with a final check as a copyrighted document. We want to make sure everything is accurate and precise. So we'll go through our internal review, and then be posted in the next couple of days. So let's see if we've got everything. There was a question about that was a 665 question here. John, I think you answered about the USP. So I think we've answered all the questions. I think we moved that one over. Yes, that was answered. Okay, well, thank you very much. Once again, let me go back to our contact information slides. If you have any questions and you want to talk to us further, you can reach out to John Hall or Rick Shorey or both. We want to thank you for joining us, and look for a post here soon about the upcoming webinar. And we'll also be emailing all of our attendees a very quick 5-minute survey. And we look forward to seeing you all again. John or Rick, do you have any closing comments?
Thanks, everybody.
Thank you.
Thank you very much. So at this point, have a nice day. We'll be talking to you again soon. Bye.